And now I'd like to present Sam Scher. Sam is the Senior Geochemist for Corescan, a hyperspectral core imaging service provider based in Perth, Australia. She received her BSc and MSc in Earth and Planetary Sciences with an emphasis in geochemistry and volcanology from McGill University, Montreal, Canada. In the past 8 years, she has worked in the mineral resource sector as a geochemist, most recently exploring the linkages between geochemistry and mineral spectroscopy, including their integration in 3D models and big data programs in exploration and mining. Sam will share with us mining applications of continuous hyperspectral data. Sam, please.
Hi, everyone. Thank you, Helen. So I want to start this by thanking my colleagues at Corescan for their insight and input into the talk, as well as to Tom Carmichael at Solve Geosolutions for his initiative for all interested women to learn how to code in R, and finally to Chile Explore for inviting Corescan to speak in the session. So I think this is, sorry, Helen, but can you see, okay, this is the right, okay. Excuse me, guys.
Yes, we can see your screen, Sam.
Okay, I was looking at this and it looked a little weird. So to start, I just wanted to say, so the title, I think is pretty interesting, something that I would have never really foreseen, a few years ago when I first started here. And I just wanted to kind of preface this by saying that the true objective of this talk is to empower users of hyperspectral imaging data to use their data in novel ways, and to continue to bring geoscientists towards integrating not only just hyperspectral point data, but also the image data that's provided, and not just the RGB, but the hyperspectral images themselves, integrating them into their projects. And whether they're tricky or they're more simple porphyries, there's a lot of information in this data, and I just hope that after this talk, everybody that's here with me can just, start thinking about using their data in different ways. So to start with, historically, modes of test work selection for GeoMet were definitely a bit more limited, and I would argue a bit qualitative because we were integrating perhaps just geological logs and the limited assay data that we had available, and we use this to demarcate similar lithological units. At present, more mines certainly have integrated a lot more quantitative data sets such as geochemistry, mineralogy, in addition to those before. However, geometallurgical domains based on the above information, as well now as on the spatial textural location of problematic mineralogy in particular, provided by hyperspectral imaging data, that certainly is the next frontier. Geomet and recovery, gangue mineralogy and recovery. So selecting test work samples based on ore mineralogy and chemistry alone risks for not accounting for how this gangue mineralogy, particularly maybe the problematic ones, how they're distributed. Geomets, geoscientists are definitely aware that if you have swelling minerals, this increases volumes in wet circuits. Biosilicates in particular may impact fluid viscosity. In particular, some phyllosilicates may consume reagents. So there's a lot of issues here with the gangue mineralogy. And particularly the phyllosilicates and other gangue mineralogy may be difficult to distinguish visually and chemically, but hyperspectral imaging can assist in distinguishing not only these minerals, but particularly also their spatial distribution. So I just wanted to throw up a little bit of geochemistry here. So if we, even with just the geochemistry, if you're looking at this here, and this is a very common plot that geochemists will use, whether to track potassic or albitization, you can definitely see the trends that are happening, but you can't particularly see necessarily the particular mineralogy. And when you start to incorporate this hyperspectral mineralogy, particularly the density and the higher resolution towards the end of the shortwave infrared that you can see in the hyperspectral imaging systems, that's when you start to see some of this mineralogy that may be invisible to the eye, but also, as you can see on the left, invisible to an extent with your geochemical data. So first, I just wanted to say, I think it's a bit of something that I think a little bit about, difference between, connoisseur, sub-air, like how you know things. And I just wanted to say, don't fear the gang, just know it and know it better. So the first thing that I think when I look at this interval, and this one was pointed out to me by one of my colleagues, and I thought it was particularly interesting. So when I look at this rock up here on the left, I see something that's whitish gray, a little bit of yellow, unclear to me particularly what they are. So using hyperspectral data, you can start to really get to know this rock a bit better. So I'm going to bring this out slowly for emphasis. So in this 30 centimeter interval, you can see that you have montmorillonite towards the left, then a bit of a sharp contact where you start to bring in porphyries, bit of mixing with porphyries and keolinite, and then just some pixels that are more pure keolinite. So you can see just in a very short amount of time and space that you're changing the mineralogy and also the way that it's potentially going to react when you bring it through a geometallurgical circuit. I wanted to bring this back also just to pure mineralogy and to spectroscopy and how this all relates into geomet. So I'm just going to, before I start talking about the spatial component, I just wanted to bring it back kind of to fundamentals a little bit, maybe a little bit for fun too for everybody, a little bit of flavor. So the basic crystal structure that you're looking at here when you're trying to know your gang a little bit more. So taking montmorillonite as an example. Montmorillonite has a basic TOT structure where you have the octahedral aluminum layer or the O sheet bounded or sandwiched between two T sheets made up of silica tetrahedra. Just a really quick note, this is before we talk about the spectral component of the montmorillonite. This is just a representation of the V-near through to the shortwave infrared. And this is just the bonds that, the ranges and the bonds that we're identifying with the Corescan system, but also in other systems as well, whether it's point data or in other systems. So particularly for montmorillonite, the ones that we're going to focus in on would be the ALOH features at 2200. It's going to also be the water features and the hydroxyl features. So looking at this to the left, spectroscopists can easily speciate these dioctahedral smectites and actually tell them apart from each other. Montmorillonite, we have in orange here, and you can see what I was talking about before in the previous slide. You can pick it up in the 1400 nanometer range, the octahedral, the hydroxyl functional group at about 1910 nanometers. You're picking up the absorption feature and the water feature, and I think the more famous one where you're also doing some speciation, the 2210 nanometer function for the ALOH group. But then, the other dioctahedral smectites, you're looking at notchnites, betalites, all of which are acting differently in metallurgical flow sheets and circuits. So, a little bit of flavor for the talk. Some advanced crystal structure that's definitely applicable to this talk. The sheets are held together loosely by weak van der Waals forces and electrostatic forces, which allows particularly penetration of water and exchangeable cations, which results in its swelling. So the connection here in a geomet are these substitutions and swelling that I just described can produce significant problems in the MET circuit because of this swelling. And even at relatively low concentrations of montmorillonate in the system, which you can see on the left in this in this diagram, where at a clay content of about 10% montmorillonate increases the yield stress significantly. Moving to this next frontier, which is kind of I think the fun part of the talk. I want to talk a lot about the importance of texture and how we can take these, how we can start to quantify this texture in terms of numbers and how that can go and flow right into how you would domain these sections, and then consequently how you could use this domaining in your planning for your geomet sampling. So the question here is, how are these minerals spatially related and distributed? Okay, so as you remember, here's that core photo that I showed earlier, montmorillonite, porphyry, keolinite. And how will the results of this algorithm impact the geometallurgical domaining? I simplified that, or maybe not so simple, but something that a lot of you, I think, that are watching this talk have seen before. So here you have this false color hyperspectral imaging map. How do you go from a hyperspectral image into making it into something that's more, say, quantitative, that a computer can interpret, say? So what we're looking for here is mineral associations, and what we want to know is how these minerals are connected to each other, and how it tells like how they're spatially distributed. And in the end, this domaining, what we're going to be doing, how do you plot this in a metric that which you can do the domaining, and then you can put it into, say, whether it's a geological strip log or start to look at it in 3D space. So this is the focus of the talk. So to the right here, this is just an example of a gray level co-occurrence hyperspectral image maps, and something that I think that when you look at these are individual mineral maps, and what you look at here, maybe you think, okay, this looks a bit like a vein texture here below it. Maybe this is a bit, you could call it, maybe if it's sulfide disseminated, or if it's it's a matrix dominated texture. So all you're doing in this image analysis work is you're looking at how the statistics of pixels are connected and spatially distributed. It's possible to extract some statistical measurements of this mineral texture from these hyperspectral imaging maps. The statistics then can be classified, can be used to classify mineral texture in both supervised classification and, importantly for this talk, in clustering applications. And something that I want to stress, and what I'll be doing in the next slide, is we have to focus the data as well. Because as anybody that's seen, that has looked at hyperspectral imaging data before, you can have upwards of 40 minerals, particularly if you're working in a skarn. A lot of porphyries have 15 minerals, and that's not even accounting for when there's different spectral parameters, different compositional parameters, say white microcrystallinities, compositions. So it can get really almost out of control very quickly, say, if you're doing something along these lines. So in terms of what I mean by focusing your data, so, the starting point for all this are the geologists, the geoscientists, the geomets from the project, the people that have the most information about where this information is originally originating from, originally coming from. And then you have the spectral geologist, which has their own insights into the data because they've been looking through it. They really understand the mineralogy and what's coming out of it. And then you have the data scientist. And what the geoscientists and the geomets will be doing, the spectral geologists, is that the geos from the project will be saying, hey, I know from my recovery, after looking at the data, that I'm definitely going to have a problem with, for example, with montmorillonite. Spectral geologists will then say, okay, well, based on this and what the data scientist is telling me, you're going to be interested in using wavelength ranges between around 1900. So use those bands, use the 1400, and use the ones at 2200. And that will make your outputs for your inputs, and then your outputs for the data scientists to be just much better, much more tight. So here is kind of one example of a workflow that a data scientist, if they're using, for example, I'm carrying through the GLCM example. So what they'll be doing is they'll be using the individual mineral maps from the hyperspectral data cube. They'll be saying, okay, for my texture algorithm, what this is going to be doing is the algorithm will be saying, okay, here is the pixel of interest, and now I'm going to see how it's connected to all the pixels around it. And then for the next pixel, it's going to be doing the same thing. And it's going to iterate over and over and over again for the entirety of whatever scale we've said to be important. Some examples of outputs, and outputs there will be many, but some that I think are a bit more easy to grasp would be something like a mineral correlation. which is describing how the minerals, how connected the mineral texture is. So if you have something like a vein, you'll have a high correlation. And if you have something a bit more massive, something that's disseminated, then you have a lower correlation. Now putting this into the context of a domaining, what you're going to be doing. You have a large data set now, a lot of different outputs that maybe aren't so easy to understand, but are nonetheless important results. So your next step is you're going to be doing a dimensionality reduction, and then you'll be doing the clustering. And just really, really simply, the dimensionality reduction is just to take it from all these variables, and you're going to just put them down so that you can view them in similarity space. Points that are going to plot together, they are similar, and plots that point far apart are dissimilar. And then the clustering is simply points that are grouped together. A mathematical equation will calculate the optimum number of clusters for you. And really what I just mean by domaining this is that if you have hyperspectral imaging data, instead of just using that point data, you're also going to be using all this image data as well. And it's just going to make your entire clusters more robust. Also, you should be, if you have geochemistry data, if you have, any kind of other downhole data, whether it's, MagSus, all these things should be just more holistic. This is just another layer on top in the toolbox. And it's just going to provide, like I said, just additional layers to this domaining, which in turn could provide key insights on your geometallurgical testwork sample selection. And really what's happening here is just you're going to have a geometallurgically similar unit, which I'm trying to show you guys with just that green unit. And this little 30 centimeter interval is coming from this unit. And the idea is that all the other points that you could take to make a good composite in that interval will all be geometrically similar, because you've had the geoscientists working together with the spectroscopists and the data scientists to achieve the best result. So your geometallurgical test work, to sum up, your test work samples, they should be coming from the location of where, starting point of where you're recognizing your mineral presence, then you're understanding your mineral and textural distribution for a very specific test work, and incorporating elements from your geochemistry and any other parameters that you have, and just making it as robust as you can, which will allow you to perform your next step, performing the appropriate test work. This is a whole nother can of worms that we're not going to talk about now. And eventually what this will help you do is optimize your flow sheet and give you an improved resource model. Thank you.
Thank you very much, Sam, for a very interesting presentation. We have a question for you. What are the common misconceptions around the utilization of hyperspectral, what are the common misconceptions around the utilization of hyperspectroscopy analysis?
Honestly, I think it's that in the veneer swirl, you can identify carbonates. I get that question a lot. There's a lot of misconceptions about the minerals that we can and cannot identify. I don't know how many questions I have in there. I think I gave a lot of information, but I think really it starts with that. And if you talk to, whether it's the index booth with Sasha, if you talk with the guys at TerraCore, if you talk with anybody in the industry, I think there's just a misconception of what can and cannot be identified in the veneer swirl, and then how the mid wave, and then how the thermal, the long wave infrared, how that can, what the capabilities of that is. So I think a lot of the questions I get at the booth are really mineral related and what we can and cannot identify.
Thank you, Sam.
Yeah.
It looks like we have another question coming in. It says, thank you, Sam, for the talk. Punctual spectral analysis, not hyperspectral, can be a good point to start for geometallurgy domains?
Hypospectral? What? Sorry.
Yeah, so they're saying whether punctual spectral analysis, not hyperspectral, punctual spectral analysis can be a good point to start for geometallurgy domains.
So I think what they mean is point versus hyperspectral imaging analysis. Absolutely. I think that when you start to think about you have to think about what the goal is of your study. And if the goal involves particularly something that involves textural analysis or the relationship between minerals, or just in general, when you're doing hyperspectral core imaging with Corescan, for instance, we have 200,000 points in 1 meter. So if there is just, a lot of, say, mineral mixing, a lot of just different mineralogy, if you have certain minerals that you just can't pull out in point data, because the systems are also just a little bit different. Each system is a little bit different in what it can and cannot do. I would always recommend that you would try out both to start with, but you can absolutely use point data. I think it just depends on what your question is. So that's why setting it up, like any good study, setting it up from the get-go of what your question is, what you're trying to achieve, and maybe as well after you've done a hyperspectral imaging study and you really can then reformulate your question better to answer whatever it is you're trying to do, and then you recognize that point data is just the way to go. It's all, we like to think of it as one big ecosystem where all different types of spectral data, whether it's airborne, satellite data, point data, hyperspectral imaging, it's just different scales. So it really has to do with your question. And I absolutely think that point data can help in doing a type of geometallurgical domaining. And I think that Sasha afterwards will probably talk about that too.
Thank you, Sam. I have another question from the audience.
Sure.
Awesome talk, Sam. Suggestions for legacy projects with little chemical or spectral data?
Scan it. We're pretty, with me and my colleagues, we just like to see everybody's data. It's just fascinating. Look, again, it's what your question is. There's limitations to all different techniques. I'm a geochemist as well. So, in whether it's point data, whether it's hyperspectral imaging data, there's definitely limitations on the technique. So if you're looking for the answer immediately to your gold grade or your copper grade, you have to do geochemistry too. I've been working a lot about the integration of geochemistry with hyperspectral data. And there's other people out there that have done this type of work, and they published on it as well from in academia, a few outside of academia as well. So you can write to me and I can provide you with some of those papers. But again, it really depends on your question. But if you have legacy, we do a lot of legacy projects, and the results there are always pretty interesting, especially for cryptic mineralogy. Because as well, it comes down to the fact that there are certain questions that geochemistry can't answer either, and there are certain questions that hyperspectral can't answer. So there's just this marriage between the two that's pretty beautiful. So yeah, if you want to talk to me about what we would do in a legacy course situation, come to the booth and we can definitely talk about that. But yeah, again, it comes down to the question.
Thank you, Sam. We do have some further questions from the audience, but in the interest of time, we will forward these questions via email to Sam and she can respond in turn. Thank you very much, Sam, for your time.
Yeah, thank you.
Very interesting presentation.